Well, we see that Google is proposing a scale change that wasn't even being discussed a few months ago, moving artificial intelligence computing off-planet. This proposal isn't presented as an imaginary concept, but as a concrete infrastructure design. The idea they present is that massive machine learning and inference workloads would run in orbit via satellite constellations powered by continuous sunlight and interconnected with high-bandwidth optical links. And this is where Project Suncatcher comes in, this new Google project. We say continuous because in sun-synchronous orbits near dawn and dusk, solar panels receive practically constant radiation. Unlike Earth's surface, up there are no clouds, humidity, or nights to interrupt power generation. And the weight is also reduced because this lighting setup requires fewer heavy batteries, which are expensive to launch. What they propose isn't a giant satellite, but rather a large group of relatively small satellites flying in tight formation. In the models they describe, a reference configuration uses 80 units within a 1 kilometer radius. The distance between neighboring satellites ranges from tens to hundreds of meters. This proximity isn't just for show. It allows the laser links to operate at the bandwidth needed for the cluster, which functions as a distributed supercomputer. The other central pillar is silicon. It's used in TPU, processors designed for training and inference in learning models. And newer generations like TPU version 7 push memory density and bandwidth far beyond previous versions. And that efficiency per watt enables computation at that level to be considered for orbit. Plus, when these units were exposed to radiation doses, equivalent to several years of emission, error rates stayed below thresholds that conventional correction mechanisms can handle. Tests exposed them to even higher levels than expected in typical missions without causing permanent failures in the samples. But nothing holds up if launch costs aren't solved. If the dollars per kilogram metric for putting mass into low orbit falls below $200, the annual energy cost of launching solar panels starts to look comparable or even competitive with ground-based centers. The analysis they present uses historical launch price reductions and estimates that if a certain industrial learning rate continues, we could reach that threshold around the mid-2030s. Even slightly worse levels like $300 per kilo would already have meaningful impact. For us, the key argument is that all other major obstacles, radiation affecting chips, bandwidth between orbital swarm nodes, and energy availability in sun-synchronous orbit, have been initially modeled and tested with positive results. What remains is engineering and economics, not prohibitive physics. The proposal doesn't claim there are no unsolved problems. Issues like thermal management in vacuum, orbital repairs, and downlinking useful data to Earth still need solutions. But the route they define is no longer framed as an isolated theoretical experiment. It begins with real hardware. That's why there's a concrete milestone, launching 2 test satellites in early 2027 in collaboration with Planet Lab. These prototypes will validate the actual behavior of TPUs in orbit and compare optical links for units performing distributed learning tasks. The approach we're taking here is that perhaps the next leap in infrastructure depends not just on chip design or architecture, but on where we physically place computing resources. If the trend of decreasing launch costs continues, building supercomputers directly next to solar sources could shift from being marginal to becoming a rational deployment strategy in an era where AI is considered essential infrastructure, just like electricity. So yeah, let me know what you think about this. Obviously, this project still seems quite far off, but that doesn't mean we should overlook it, so I hope you found this interesting.